start talking about the jointly distributed random variables and how we can describe the independence between them or the joint characteristics of the variable, either they are correlated or uncorrelated, statistically independent or dependent, or the orthogonality of the random variables. So I'm just like gonna revise very quick on what we did last time. So last time we started talking about the covariance between two random variables x and y, and then we said that this covariance is equal to the expected value of x multiplied by y minus mu x and mu y. And the covariance is like has the like, let's say that we are talking about height and weight. So if the height like is the mu, what is the average of the height of the students in this class? So this is going to be mu. What is the average of the weight of the students in this class? Is going to be mu y. So the final unit is going to be meter by kilogram. It's going to be pound by foot. So it's going to be have some units here. So that's why in statistics, sometimes we use like a normalized value. It's called rho xy, and this is the covariance. This is the coefficient of correlation coefficient. So the correlation coefficient between two random variables x and y. This is going to be the covariance of x and y divided by sigma x sigma y. Then this is one of these, or maybe both of them are the only way that we can know the dependence or the correlation between two random variables. So, and we had 3 cases last time. Case number 1 was if we have uncorrelated random variables, sometimes we call this linearly independent. That's when the coefficient of correlation rho xy equal to 0, or the covariance of x, y equal to 0. And that means that the expected value of x, y should be equal to mu x mu y. And if two random variables are statistically independent, so for statistical independence, if you guys know, if we want to describe the PDF, the probability density function between two random variables, we usually, and if they are like dependent, so we just like write something like this, the fxy, something like this. But if they are independent, so the fxy is going to be equal to the multiplication of the 2 PDF of each two random variable. That means that they are separable. You can't separate them. So that's the function, the PDF of the two random variables, fxy. So basically, if you know this, you can substitute here and getting the expected value of xy by substituting this function. And as we know that the expected value are always equal to the two random variables xy multiplied by the fx dx dy, and this is double integration over x and y. So this is how to get the expected value of xy multiplied together. But what if x and y are independent, statistically independent? You can write it that way. So this is going to be basically if x and y are statistically independent, so you can say that the expected value of x y is going to be equal to the integration of the two functions multiplied together. And now we can separate fx and fy from each other. And if x and y are functioning the same variable, like let's say that you have x is function of gz and y is function of hz. So basically, you can make all this function in z, and then you convert it from double integration to like one single integration. All right, so this is for statistically independent random variable. And also we talked about the orthogonal random variables. So for orthogonal random variables, we said that these two random variables has nothing to do with each other. There's no correlation. Like our random variable x is going that way, and our, like if we plot the data, we're gonna find the data, some of it like follow x, some of it follow y. So they are perpendicular to each other. They have nothing to do with each other. So that means that the expected value of x, y not equal to mu x and mu y is gonna be equal to 0. It's something like you are doing, as I said last time, like you are doing dot product. So when you say, if I have a vector A, multiply dot product with vector B, that equal the magnitude of vector A multiplied by the magnitude of vector B multiplied by cosine theta between them. And if theta is equal to 90 degrees, this value is going to be equal to 0. And that's what is our data is. Like you have x is going that way, the other one is going that way. And that's actually the definition of orthogonality in math. So if anything is orthogonal, that means that they are perpendicular, or the angle between the two vectors are 90 degrees, and if it's 90 degrees, cosine theta is going to be equal to 0. All right, so how we are going to use this? So basically, in the exam or in the homework, I would give you a function of x. I give you x and I give you y, and both have a function of a specific variable. And I will ask you, find the correlation between the two random variables, or find the statistical independence. Find out if they are statistically independent or not. Find if they are orthogonal or not. So let's solve an example and see how this is going to work. So all right, so here so in this example, I give you a function z is uniformly distributed, like I said, z uniformly distributed on 0 and 1. So when I say that you have a random variable is uniformly distributed from 0 to 1, that's basically you draw on x-axis your random variable, and on y-axis the BDF, fz of z, that is the BDF. And if I say the uniform, that means it's a constant. So it's going to be something like this. From 0 to 1, and this is definitely is equal to 1. Why? Because the area under this curve should be equal to 1. That's the total probability. So the probability of z is going to be always equal to 1. It's not varying. That's what uniform distribution is look like. So uniform distribution is one of the easiest distributions. All right. So you have basically, I can say here that fz of z is equal to 1. It's always constant. Maybe sometimes I'll give you a curve, I'll give you a low normal distribution, I'll give you a normal distribution. So f of z is going to have a function, it's not going to be constant. Okay, so that's z, and I give you x, two variables, x and y. And I said that x is equal to sine 2 by z, and y is equal to cosine 2 by z. And my question here is, check the correlation and statistical independence. Check. correlation and statistical independence between X and Y. Let's find out. All right, so that's the 9 questions. So what you are gonna do to find out, first, you have to find what is mu X, what is mu Y, what is the expected value of X and Y. Once you find these 3 quantities, first you are gonna check for uncorrelated random variable and try to find if the expected value of X, Y is equal to mu X, mu Y. And then you are gonna check for statistical independence. So you are gonna try to find if they are, and then you can check for orthogonality, okay? But let me ask you, do you think X and Y are statistically independent or not? Like from, when we say statistical independence, that I mean like there is no way that you can relate X to Y. There is nothing that can group them together, or is nothing that can make together equal to something. Like they have nothing to do with each other, okay? But all the trigonometric functions sometimes have something to do with each other. That's how we drive them. They are coming from the same triangle, right? So the thing is, we can say if you find sine and cosine, or if you find a trigonometric function, there's definitely a way that you can make them depend on each other. And we all know what is the function that can get sine and cosine in one function. Do you guys know it? There's one function that has sine and cosine, and they are equal to one something that we all know.
Sine square plus cosine square equal.
Exactly, excellent. That the sine square of a theta plus the cosine square of theta is always equal to 1. So there is something that can group these together. So they are dependent, okay? They are not independent, okay? So that's something for sure that we know, that there's an equation or there's something that can group them together. It's not like you are rolling the dice and flipping a coin. They have something to do with each other. So that's what we know for sure. So from my perspective, they are statistically dependent because there is an equation that can group them together like they are. There is something, if I make sine 2 pi, sine squared 2 pi z plus cosine squared 2 pi z, we all know that this is always equal to 1, right? Sine squared plus cosine squared is always equal to 1. So since they have something that can get them together, so they are statistically dependent. Okay, so let's check the other 2 checks, the uncorrelated random variables or the orthogonality check. Okay, so to do this, I have to find first the 3 things. I have to find mu x, I have to find mu y, I have to find the expected value of x and y. Can you guys find what is the value of mu x?
Expectation of x.
Is the expectation of x, and this is going to be equal to the integration of x multiplied by fx of x dx. And also this can be equal to, if you guys remember, if x is a function of a random variable z, we can, if you guys remember, we had like a rule, x is going to be equal to z or gz. Like you substitute if x is a function of something multiplied by f z. Oh, we didn't have it this way. It was not this way. We had f x of x dx is equal to f z of z dz. Do you guys remember this? And it was fx of x is equal to f z dz dx, or f z of z is equal to fx dx dz. So it's going to be the same thing. So I can write this in a different format. I can substitute with x with this, which is gz, and I can put f z of z dz. It's the same thing. All right. The thing is, for x, I don't know what is the boundary of the integrations. I know the boundary of integrations. I know that fz is from 0 to 1. That's the boundaries. If you want to find out what is the boundary of x, You substitute with z equal to 0, so sine 0 is going to be equal to 0, and substitute with the z equal to 1, and then you are going to get sine 2 pi, and also it's going to be equal to 0. It's going to be a messy integration. But here, I know the boundaries of z. I know that z is distributed from 0 to 1, right? So everything is functioning in z. So let's do this integration. I want to integrate from 0 to 1. Gz is equal to sine 2 pi z dz. Oh, you guys know what is the f z of z?
1.
Is equal to 1, and here I have dz. Okay. So can we do this integration? So what is going to be? The integration of the sine is
Minus cosine.
negative cosine, so I'm gonna have here. But the thing is, I have 2 pi here, so I have to put here negative 1 over 2 pi, and then I'm gonna have cosine 2 pi z from 0 to 1. Is that right?
Yeah.
I have to divide on this, and then I'm gonna have negative 1 over 2 pi, and then I substitute with the boundary of the integration. So this is gonna give you, if you put z equal to 1, so you're going to end up with cosine 2 pi. Cosine 2 pi is equal to 1, right? And then you substitute with the end boundary, so it's going to put 0 here. So cosine 0 is also equal to...
First one, I think, minus 1.
So cosine 2 pi is equal to 1.
Yeah, it's 1.
It's like 0. It's like 2 pi is like you are coming to 0.
Negative 1 or 1?
I think it's 1.
No, it's 1. It's not t.
Yeah. Okay, so we have here the cosine.
Negative 1.
It's gonna be 1, and if you put here 0, this is gonna give you cosine 0, so you're gonna have end up with minus 1, and this all is gonna give you 0.
I think first one is negative 1, negative 1. Cosine 108.
It's not 180, that's 2 pi, that's 360.
Oh,
So 2 pi is 360, that means like the same like 0. So here, that's cosine 0 is equal to 1, right? Then here, cosine 90 degree is equal to 0. Then 180 is negative 1. Then 270 is equal to 0. And then here, you come back to the 0 again with 360, it's gonna give you 1. So cosine 2 pi is equal to 1, and cosine 0 is equal to 1, so you end up with 1 minus 1 is going to be equal to 0. Okay, so the second thing, you need to find mu y, and mu y, we're going to do the same thing. It's going to be the integration of y multiplied by fy y, and then we're going to substitute with the gz's multiplied by fz of z dz, and definitely from 0 to 1, and here I can put the integration from 0 to 1. Gz is equal to cosine 2 by z, and I have fz is equal to 1. It's a constant function, so I can put here 1, and then I'm going to have dz. All right, so let's integrate this. The integration of the cosine is sine, so I can have here 1 over 2 pi sine 2 pi z, and I need to integrate from 0 to 1. So that's a very easy one. I know that the sine 2 pi is 0 and the sine 0 is 0. So this is going to also give me 0. So mu x and mu y are equal to 0. So let's get to the difficult part. The expected value, I'm not sure if this is going to be enough to do it. But let's divide this space into 2 parts here. Let's find the expected value of xy. The expected value of xy is going to be equal to the double integration of xy, fxy, dz, dx, dy. That's what we had here, okay? All right, so let's put x and y. So this is going to be, x is going to be equal is a function in z. So this is sine 2 by z multiplied by cosine 2 by z. And the thing is, since both are function in z, I can make this as a one single integration by putting the distribution of z and this is going to be dz, and this is going to be one integration from 0 to 1, since they are all function in z. Okay, this is a little bit difficult integration, but I'm not sure if you guys have ideas from like the maths when you guys studied. When you have sine and cosine, or if you have integration of two functions, you try to manipulate one to look like the differentiation of another one. Like, okay, so the thing is, if we try to find out, or if we try to make this function is the differentiation of this function, like if you differentiate the cosine, actually let's make it the sine, it's going to be here, the integration from 0 to 1. And if I try, like if we say here this cosine 2 by z, and okay, and then here is the, if we try to find the integration or the differentiation of this function is going to be 2 by sine 2 by z. This function is the same like this function, but I have 2 by inside, so I have to put 2 by. So basically, this function, this, what I wrote here is the same like this, but I just put 2 by here and 2 by here. So if you take them out, it's going to be the same. So the thing is, what we are going to do is, and actually here's these, all right? So if you go and revise how to integrate two functions multiplied together, you make one of these functions differentiation outside. So when you integrate, we do something like this. We put this as u, and we said that u is equal to cosine, the main function, cosine 2 by z. And if we want to find du, it's going to be equal to, if you take
negative 2 by sine 2 by z.
Sure. This is cosine 2. Oh, sorry. I think here this one is wrong. I need to make this one is the main function and it's differentiation outside. Actually, you can do both the same, but here I have to put this as negative. Like I can do it that way, but it's going to be different from the notes. So if I want to make this, like this differentiation outside, so the differentiation outside, this doesn't need to be negative 2 by, because that's the differentiation of cosine 2 by z. If you differentiate it, it's going to be negative. But if you make the sine and we make the differentiation out, so it's going to be the cosine positive. But since I put negative here, I have to put negative here. This is going to be a little bit different from the notes, but it's going to be the same thing. Okay, I'm going to try it. I'm sure it's going to work. And here, this is cosine, so du is going to be negative 2 by sine 2 by z, and you are going to have dz, right? So if you want to substitute and make all this as a function of u, so this is du and this is u. So I can basically write this as negative 1 over 2 by the integration. This part, negative 2 by sine 2 by z dz is equal to du. So I can put du outside by removing this and this. And this part is u. So basically this is a function that you can integrate. So this is going to be equal to u squared over 2. So you're going to have negative u squared over 4 by. Because this is going to be u squared over 2. And you have negative 1 over 2 by. So it's going to be something like this. And you have to put the boundaries of the integration. But the thing is, once I'm done with the integration, I need to bring it back to its original form. So I can't substitute with the form of u, so this is going to be equal to cosine squared 2 by z over 4 pi, and you have to integrate this from 0 to 1. The thing is, you are going to get back to the same original thing, like cosine of 2 by 0. Cosine of 2 by is going to be equal to 1, and cosine of 0 is going to be also equal to 1, so it's going to give you also 0. The thing is, the way that I did it here, I did it the opposite. Rather than putting the differentiation of the cosine outside, I put the differentiation of the sine outside, but you are not going to see the negative, but it's going to give you the same answer. All right, so right now we have everything is 0. Mu x is 0, mu y is 0, and the z also is equal to 0. You guys know why? Because the sine is something like this. Like this is the sine, it's something, or the cosine is something like this. So when you take the mean, it's 0. And also the same thing with the sine. When you take the mean, the thing is you have a positive area and a negative area, and both they are equal to each other, so their mean is equal to 0. Okay, so, all right, so what we have here, actually, we have the expected value of xy equal to mu x multiplied by mu y. So that means that the two random variables are uncorrelated random variables. And also, we have the expected value of xy are equal to 0. That means that they are orthogonal random variables. So they are orthogonal and uncorrelated.
How they can be orthogonal? They are the same axis, same shape, like they.
I mean, the orthogonality has nothing to do with each other. They don't affect each other. I mean, like they have nothing to do with each other. Like this is have completely different shape from the other one.
Okay.
Okay. But anyway, that's what the function. It's a little bit weird function because everything is equal to 0. Like you'll say, okay, mu is equal to 0, so there's nothing. Like, but because you have a complete area positive and a complete area negative, it has values. But the values are like they are like making each other zeros. Okay, so with this, let's move to a new interesting topic, which is the different distributions that we can represent random variable with.
Could I ask a question about the integration in the beginning of x?
Here?
Yeah, no, in the beginning, yeah.
Hmm.
So you transferred the function to z because I already have the probability of z as uniformly distributed and I don't have any information about x.
Yeah.
Is that the reason?
Yeah, because that's actually the general function. But the thing is, you don't have fx and you don't have an x is not a variable by its own. This is its function in z, and fx is you also can get it as a function of z. Okay, because since you have z as uniform, so you can substitute in this one and make everything as function in the random variable that x is function in.
I mean, if I want to solve it with fx, I can't because I don't have the.
Because you don't have x. What is the value of x? This is the value of x. That's how we do it. If x is equal to 2z squared, you are going to put 2z squared. If x is equal to 10z plus 5z squared plus z cubed, you are going to put it here.
That's it. And if I solve it for x, the boundary condition gonna be different. It's not gonna be from 0 to 1. It's gonna be the intersection between the sign and the function.
Yeah, you have to go through the integration, the whole integration.
Okay. Thank you.
All right. So, I believe the last topics that we have to finish the theoretical part is the common probability distributions. And the first distribution that we are going to study together is the normal distribution, the most well-known distribution. The thing is here, we put a distribution to z, and that's a uniform distribution. That's also a known distribution. Sometimes your data are all uniform, all having the same, like you might take some cubes to the lab and you were able to, when you like make your concrete mix to make it very uniform, and you did it very good in the lab, that gives you almost a uniform number. Like all your numbers, I mean like not exactly the same. Actually, usually the uniform distribution is something like this, like something like this. It's not like a straight line, but it's something like this. There's a little bit of variability, but it's still a uniform distribution. You can't represent it with a straight line. So that's when you have almost you were able to control, and that's when we talk about the types of uncertainties. There's uncertainties that you can't control, and you can reduce them by controlling the parameters, controlling everything in your mix, or controlling the experiment. You might not get the exact number, but it's going to be very, very close to deterministic. It's like, if you guys remember when we draw distributions, some distributions are like this, and some distribution like this, and some of them are like almost one single number. The more that your distribution is a spread, that means there's a huge uncertainty. The more your distribution is coming together and being like a single one point, that means it's getting to be deterministic. Okay, so that's what we were talking about before, but let's start with the normal distribution. Okay. As you guys know, there's two types of normal distribution. There's the regular one, and there's one is called the standardized normal distribution. So we're gonna know the difference between them right now. Normal distribution, it's like I tell you that the mean of our age here in this room is like 35 years, or the mean of our height is like 5'8" or something. So I give you mean equal to specific numbers, let's say 6, and sigma is equal to 1.2. That is the normal distribution. In a little bit, we are gonna discuss something it's called standardized normal distribution. What is the standardized normal distribution? It's basically we take this normal distribution and standardize it and make the mean equal to 0 and sigma is equal to 1. And I'm going to tell you, so all the distribution that you are going to have for all the data, they all are going to have mu is equal to 0 and sigma is equal to 1. Usually our data is coming in a regular normal distribution, but to solve it, we take it to a standardized one, and once we finish our solution, we take it back to a normal one. And we're going to see this in solving problems. Okay, so I give you mean and mu, and basically this distribution is something like this. Let's say I put 6 here, so let's say this is 6, 7, 8, 9, 10. We go back 5, 4, 3, 2. That's how the normal distribution look like. And this is the PDF, as we all know. So this is fx of x, and this is our variable x. And if we take the area under this curve, it gives us the 1, which is the total probability of all the expected, the values of x. Okay, so this function can be written that way. It's basically 1 over the square root of 2 pi of sigma x squared multiplied by the exponential of -1 over 2 x minus mu x over sigma x all squared, and I have to close this parenthesis. This is the function of this curve. So if you want to find fx at 5, you substitute with mu and sigma, and x is equal to 5, and then you find the value of fx. And as we all know, this is the PDF. We usually, when we have random variable is normally distributed, this is how we write it. Like we write that the random variable x is equal to this is how we write it. Like if in the exam I give you a simple theme or something, and I told you this load is 1.5, that means that this load has a mean, is a normal distribution, and its mean is 6 and standard deviation is 1.5. So that's the standard of how we write the normal distribution. Okay? All right, so if we want to write the fx, it's basically, we have to integrate, like if I want to find, this is the PDF. If I want to find the CDF, like at x equal to 5, this is goes to infinity, and this is goes to negative infinity. And if you want to find the CDF, you basically take the area until the number, like let's say I want to find f(x) of x, that specific random variable. You integrate from negative infinity until this variable. My variable here is 5, so you put 5 here, and then you integrate this function, which is equal to By the way, guys, please check the notes because I believe I forgot to put the square in the notes, the one that are online. So try to ensure that it's a square. And here you're gonna have the exponential of negative 1 over 2x minus mu x over sigma x whole square. And then we're gonna have dx here. Okay, so this is for the normal distribution. For a standardized normal distribution, as I said, it's going to be something like this, but rather than having the mean is equal to a number, it's going to be 0, and sigma is going to be always equal to 1. So this distribution is going to be something zero. And here you can go 1, 2, 3, 4, 1, negative 1, negative 2, negative 3. Here is negative infinity, here is positive. That's the distribution. So let's find some characteristics of this distribution. The thing is, okay, let me put the CDF. This is the BDF, the probability density function. So when it comes to standardized normal distribution, we don't use x, we use u. I'm going to tell you why we use u. And we say that the function, the BDF is phi small of u, and this one is the phi capital of u. That means like similar to f small x and f capital X. I'm going to tell you why we use u, and this is going to be u, the random variable, and this is going to be u. And when we say mu, that mu is the expected value of u, which is mu u is equal to 0, and the standard deviation of u is equal to sigma u, and this is also equal to 0. So the thing is, let's see why we did u. Like here is the function when it's like fx of x. If we want to make it a mu, basically we say that x clear. Okay, I forgot to put what is the value of u. But anyway, right. So what we do here, basically, we put x minus mu x over sigma x equal to u. All right. So if I substitute in this function with this u, is gonna be something like this. Like look at this function. Right now we have mu x, like sigma x is equal to 1. So basically if sigma x is equal to 1, this is gonna be 1. You are gonna have 1 over 2 pi. So if you wanna find the fu of u look at this function, is going to be 1 over the square root of 2 pi, and sigma is going to be equal to 0, multiplied by the exponential of negative 1 over 2, and here x minus mu x is going to be equal to u, so that means this is equal to u squared. That's basically the function. And as I said, we can name this as phi small of u rather than fu of u. And the f capital of u is going to be the integration of fu of u du, and this is the phi capital of u. All right, so let's find out a little bit find the characteristics of the standardized normal distribution. All right, so for the standardized normal distribution, if you are looking at, like, let's say I take a straight line here of phi u that has, like, if I go here at phi u and I came here and I did it's symmetric, okay? And I came here and I took a line down here and a line down here, the area here and the area here are equal to each other because it's symmetric, right? Okay, so this, we call it, like, let's say, let me read the numbers. And the thing is, the value here is going to be the same like the value here, but this one is negative and this one is positive. Like, if this is negative 2, this is going to be positive 2. So let's say if this is u1, this is going to be equal to negative u1. All right? But let me ask you, if I take these two u's down here, like if I take this here and I take this here, this is negative u1 and this is u1. That's the CDF, not the PDF. What this value represent and what this value represent?
First value represents this area, small area to the left, and
Excellent. So this area, if you try to find this area, like all the area behind this curve, is gonna give you this value. Like, let's say that you calculated this area and you find them, it's equal to 0.23. So this number is gonna be 23, not the area behind the number, this number. How about u1, this one?
u1 is the whole area minus negative the right part, or
It's 1 minus this, or all the area behind this number. So if I take all the area here, like if I hatchet all this area behind this number, is gonna get me this number, which is almost all the curve. Okay? The more that I go here, the more this number is approaching to 1. Okay? So that's what we know about this curve. So let's write this. Here, what I have, I said, and I'm gonna put something in here, guys tell me why. I said here in my notes that the phi capital that I'm looking at this curve of negative u1 plus the phi capital of u1 are equal to 1. Do you guys know why?
Yeah.
Why?
Because
Okay, let's look at the phi capital of u1. What is the phi capital of u1? That means all this area, right? What is the phi capital of negative u1?
small
Yeah,
area.
The small area, this area, which is equal to this part. So basically, this part plus this part, which is equal to this part, is equal to 1, the entire area of the curve. All right, so that's the first characteristic. And I can say that the phi of u1 is equal to 1 minus the phi of negative u1. I just send this back on the other side. Okay, so if you want to find the phi at u1, it's basically the entire curve minus this piece, which is equal to this piece. All right, so that's I believe the only characteristic that we have till now. If we want to find out the probability of, like in this curve, let's write this curve something like this. we need to find out A to B. Right, so I give you here, this is an example, or an illustration. I told you that X is a normally distributed random variable, not standardized normal distribution. And at normal, and we have mu X and sigma X. And I'm asking you, what is the probability, this is X, and this is Fx of X. And I'm asking you, what is the probability of your random variable to be more than or equal to A and less than or equal to B? That's what I'm looking for. Basically, you have to use this. If you want to find out, not this, you have to use this function and integrate it from here to here. So basically you integrate this function, Fx of X dx, and you integrate it from A to B, right? This function you integrate it from A to B, which is the f capital of B minus the f capital of A, right? But we're gonna find it out right now. All right, so if I'm gonna put this function, so this function is gonna be the integration from A to B, and if I wanna substitute with this one, it's gonna be square root of 2 pi sigma x squared, and then you're gonna have the exponential of -1 over 2x minus mu x over sigma x all squared, and I'm gonna have here dx. And what I'm gonna do, I'm gonna convert this to standardized normal distribution. As I said, if we are gonna do this, we're gonna put the u equal to x minus mu x over sigma x. And if I have it that way, I need to find du. Du is gonna be equal to 1, like if you find du dx, like if I'm gonna differentiate this function with respect to x, x is here, so the thing is when you differentiate this is gonna be 1 over sigma x, because this is x over sigma x minus mu x over sigma x. Mu x over sigma x is a constant, and then you are gonna end up with the derivative of x over sigma x. So du is equal to 1 over sigma x dx. All right, or I can say that dx is equal to sigma x du. All right, so if I want to put this here, so this is going to be the integration of 1 over 2 pi root 2 pi, and this one is going to be the exponential of -1 over half here, and here I'm going to have this as u squared, and that makes sense. I'm going to have du here. Okay, look at this. dx, I can take this sigma x squared outside. If I take it from the root, it's going to be 1 over sigma x, and 1 over sigma x and dx is equal to du, and then I can have du here. And this is going to be the integration from u1 from A to B. Okay, look here, I have A and B, which A and B are boundaries in x direction. So A and B are random variables of x, they are not random variable of y. If you want to find the corresponding y, sorry, the corresponding u, so as we said that u is equal to x minus mu x over sigma x. So if you want to find ua, so this is going to be a minus mu x over sigma x. If you want to find ub, it's going to be equal b minus mu x sigma x. So this is going to be equal to b minus mu x over sigma x, and this is going to be a minus mu x over sigma x. So this function, the probability of x to be more than a and less than b, is going to be equal to this integration. This integration, if we did it, and this is actually standardized normal distribution. So what I did here actually, I converted the normal distribution to a standardized normal distribution between these two boundary conditions. And actually from first, if I want to find it, what I do, I already know, I already substituted here with, I can find the UA and UB and put them here and try to find what is the area between these two curves. So this means the phi capital of B minus mu x over sigma x minus the phi capital of A minus mu x sigma x. It's like trying to find the probability of U, let's put a U capital, is more than UA and less than UB. So, and if this is your standardized normal distribution function of U, like something like this, and this is UA, and this is UB, and we are trying to find this area. So what I'm trying to doing, I give you a normal distribution, I give you the mean, I give you the standard deviation, and I'm looking for the probability of your random variable to be more than A and less than B. So it's going to be the same thing in the standardized normal distribution, but you have to convert A to UA and B to UB. How? By this formula. If you converted them, right now you can use this distribution. So you have to convert your whole number to normalized and then use the normalized distribution, and then you are gonna find this probability. Okay, let's put this in an example so that we
May I ask you a question?
yeah.
Under the standardized normal distribution, we will
What?
SDU is equal to sigma U is equal to 0.
One.
I mean, it should be 1.
Oh, one, sorry. So what do you want? Thank you. All right, so as I said, most of the problem, I'm gonna give you the mean and the standard deviation in a normal distribution format, and then we need to convert it the same way that we converted it. Like, let's say for example, I give you students' scores in a structure analysis are normally distributed with a mean of 78.6, and the standard deviation is 8.2. Okay, so I'm setting here example. Students scores in a structural analysis exam are normally distributed with mean of 78.6 out of 100 and standard deviation of 8.2. And I'm asking you, what is the probability of a student score greater than 81? What is the probability of student score greater than 81. I sometimes ask that question a different way. What is the student score is more than 65 and less than 85? Okay, we can ask it a different way. All right, so basically I gave you a normal distribution, and I told you that the mean of the student's score is 78.6, and they are distributed with a normal distribution, and I'm asking you what is the probability of greater than 81? Like, let's say this is 81, so actually we need the area of this part. Okay, so that's what I'm asking for. The thing is, if I give you something a normal distribution, you will not be able to solve it. You have to convert it to standardized normal distribution. I'm going to tell you why we cannot solve it, because the thing is, we don't have this function. we use, where is it? We use tables. So you're gonna have this table. This table, it gives you the area under the curve at each single number. But this is for a standardized normal distribution. You don't get it for a regular normal distribution. So basically, if I ask you what is the probability of a specific value to at a specific z, like z is like 2.1. So basically, this table is having the number like here from negative 3.4, negative 3.3. So all the negative number here. So you have 3.4, and here you have the second digit. So basically, this table is something like this. And by the way, this is for a standardized normal distribution. So let's say this table is basically trying to find the area under the curve. So if your number is, let's say, negative 1.62, so you're gonna have here, for example, negative 3.4, negative 3.3, up to negative 1.6. A lot of numbers. But the thing is, my number is not 1.6, it's 1.62. Here you're gonna find the second digit, 0.01, 0.02, 0.03, up to 0.09. Okay? So if you want to find what is the area under this curve, you go at 1.6 and then go all the way until you find 0.2, and this is the area under the curve. So the thing is, this is not a closed form solution. Like, it's not a function that like if you see here, we always have it under the integration. I never integrated this function because there is no closed form solution for this function that you can substitute with the value of x, or there's a way that you can do this integration. There's people that were trying to solve it was like a kind of binomial, this like binomial series or something, but it's still not even close. Okay, so since we cannot solve this, like we have a table that can solve it for us. And this table, as I said, you go with the number that you have, and then you pick the first digit from here and the second digit from here, and you get the area. And always the area is positive. But you will find that this table is divided into two parts. One part is for the negative area, the negative part. So you will find all these numbers are negative until you come to negative 0. And then you are gonna find the positive areas here. So if your number u is negative, so you are gonna use this part. And definitely it's less than 0.5. Like if you go here, yeah, you will find that the negative 0.09 is equal to 0.4641. But if you go here at 0, 0, you'll find 0.5, like here. This is 0.5, and then you go all the way until you come at 0.9998. If you are trying to take the probability at like 3.49, okay? All right, so we know how to use this curve, and you are allowed to take it in your exam. And right now, all right, so let's put this problem in numbers. So my random variable is x was the student's score, and this test or the student's score is normally distributed with mean 78.6, and the standard deviation is 8.2. And I'm asking you to find what is the probability of x is more than 81. That's actually all these words are in these two lines. So let's find out. The thing is, what I want to find out, I need to convert this to u. And as I told you, u is equal to x minus ux over sigma x. This distribution is based on this equation, the u1. Okay? And u, we put u is equal to x minus sigma x over x minus mu x over sigma x. Okay? So basically, this is based on this. When we substitute this and sigma and mu equal to 0 and sigma is equal to 1. All right. So right now my x is equal to 81, and mu x is 78.6. So here I'm gonna put 81 minus 78.6 over 8.2. So you're gonna find that your U is equal to 0.293. That's my U. So this is the normal distribution. If I want to find the equivalent standardized normal distribution, it's going to be something like this, and this is 0. And I'm trying to find out, this is 0.293. This is 0.293. And the opposite is equal to negative 0.293. I'm trying to find this area, right? So to try to find this area, which is, so I can say here, the probability of my X, the student score, to be more than 81 is the same like the probability of U to be more than 0.293. Are we all agree with this?
Yes.
Okay, so this should be equal to this. That's the standardized, that's the normal distribution. So that means that this is equal to 1 minus the probability of U less than 0.293, right? So all this minus the probability of this, less than, oh yeah.
Yes.
So this is gonna be equal to the whole curve minus all the thing in the behind. The thing is, this curve, this table, doesn't give you what is less, what is more than, it gives you what is less than the number. Like if I substitute with 0.293, it's gonna give me the area behind this line, not the area after. So what we do is, we get the area, the less than, and then we take 1 minus to get this area. Actually, we wrote this here, somewhere like, yeah, here. Like if we wanna find out the phi of U1, the positive one, it's basically 1 minus like the same area, the negative one, like this area. Okay? All right, so let's find it. So that's it, basically is equal to 1 minus phi of 0.293. So if I go in the curve, in the table, and I try to find 0.293 in the positive part, so I'm gonna use this part, and I go all the way to 0.2 and all the way up to 9, so you're gonna find out that this, grab this page. So you're gonna find that this is equal to 0.614. So this is gonna be 1 minus 0.614. So this is basically is gonna be equal to 0.386. So this probability, so the probability of the students to get a score more than 81 is 38%, based on the analysis that we have done here. Does anybody have any question?
May I ask? Here we wrote 1 minus P U smaller than 0.293. I mean, we don't know when U is equal to 0.293.
Yeah, you mean like the probability of, I mean, what equal to?
Exactly.
It's gonna be less different, so that's why it's not that
So
much
we-
different. So actually you can put here like this and here, so the difference is gonna be almost 0. Okay, and even the number that we got here is the number that we got for 0.29. 0.29. There's no a third 1 for 3. The thing is, you have to interpolate if you want to get that accurate. But I would accept it if you got it for like just for the second rounding. You don't have to get for the 1 to 3. All right. Okay, so the thing is, we could have done this in a different way. Rather than writing 1 minus all this, we can say that the probability of X more than 81, as we said, it is the probability, of u more than 0.293, and we said that this is phi of u more the phi of 0.293. This is equal to the phi of this is 1 minus phi of 0.293. This is equal to phi of negative 0.293. Like rather than getting the one that is positive and then subtract one, so basically if you want to find 1 minus, so this area is equal to this area in the negative part. So if you want to find the probability of more than a positive number or the probability of more than, it is going to be equal to the probability of less than on the negative side. Because like if you even come here and I told you what is the probability of a student to be here at 0.1 and want to find this area. So basically the curve gives me the area behind. So what I have to do, if this number is, let's say 0.15. So rather than doing the 1 minus, I go to the negative 0.15 and I get its phi, so it's gonna give me the same of this area. So this is a two-way to do it. So whatever you would like it, you can do it. Does anybody have any questions so far? Okay. So 5 minutes, so I'm not gonna give any new examples. I'm gonna give you different ways, like in real life, how the normal distribution might look like, or how the distribution of your data might look like. Sometimes our distributions is not like uniform the way that we have here. So data distributions Right. Sometimes our data, like, sometimes actually your data sometimes comes uniform. Like as I said before, your data, when you try to plot them, the thing is when you get your data, you don't know what is the distribution is. The thing is you need to figure out what kind of distribution that best fit the data that you have. So usually, sometimes, normal distribution is the best way to represent your data. But the thing is, sometimes there's no way that my data is negative. No way that the compressive strength of the concrete can be negative. So the negative value is never gonna exist. So normal distribution is not the best way to fit my data, and I have to look at another distribution that doesn't generate negative numbers. So the thing is, yeah, if we need to look at other ones is like exponential distributions. Okay, so data distribution is defined by their modality, their skewness, and also sometimes we get unusual features. The modality, this one is called a unimodal. Like unimodal is like your normal distribution is just one curve, unimodal. That is bimodal, like you have a normal distribution and then another normal distribution. That is multimodal, like when you get multiple peaks. Unimodal, that's uni. That's that's pi. That's multimodal. So the skewness, we talked about the skewness. Sometimes we get data that are symmetric. There is no skewness. Sometimes we have positive skewness, like this one is going to the positive. Or we have negative skewness, like this one is going to the negative. Sometimes in our data, we get unusual features. We call these outliers, okay? So that's how data in real life look like. I thought that it's quite important that you get exposed to how real data might look like. But most of our applications that we're gonna deal with in this class, we're gonna deal with something like this and usually symmetry. All right, so that's it for now, and see you guys next time to talk about more distributions.
Oh, if we have skewness, like, could we make it standardized or no?
I don't think so. You have to include it in your analysis. It's gonna be a different equation.
It's gonna be